Now, we're all well aware that for a student walking into an undergraduate abstract algebra class, they are required to have a good deal of not only knowledge, but thinking skills. Abstract algebra requires, one, an ease and generalization of patterns, concepts, and definitions. It also requires constant but unprompted mental play with concrete examples. For when you don't understand a particular concept or definition, you kind of expected to have a grab bag of things that you can bring out, and you know which ones to bring out, and you know how to play with them in your head. Abstract algebra also requires high familiarity with algebraic structures such as complex numbers, modular arithmetic, etc. It requires an ease in thinking in terms of sets and functions, and it requires previous experience with proofs. These thinking skills and content are also very necessary for students who are getting certified to teach 8 through 12 mathematics. However, these are the exact skills and content that they do not come to the class with. These thinking skills and content are also very necessary for students who are getting certified to teach 8 through 12 mathematics. However, these are the exact skills and content that they do not come to the class with. Very briefly, our idea was we scale back lecture in favor of group work on exercises. So a typical class would look like, for the first 30 or 45 minutes, Dr. Thron would lecture on the basic concepts and skills they need that they were supposed to have gotten from the reading, and make sure that that's fundamentally there. Then we would move to a time of working through examples, different directed exercises, and exercises that they could work on as groups, so they could really delve into some of the mathematics and the issues that are in the concepts. At any time when they're working on that, if it's clear that everybody is really having problems with a particular skill or concept, then we go back to lecture mode briefly and work on that. And the rest of the class was a back and forth. Now back to the textbook then. So how do we develop their skills in generalization and mental play with concrete examples through the book? Well, the first thing that we consistently did is we had them simply work with concrete examples. They don't have a grab bag of examples, and so it has to be provided to them. We have an example on the left here from the modular arithmetic chapter. I start off with the first example of that section, asking about what time to take a turkey out of the oven. The next thing that we did was we caused them to see and extend patterns through discussion / examples / exercises. In the example on the left, we do it through discussion. We show them the arithmetic that they're doing in their head, and through discussion we generalize what that arithmetic is, and then we give them a couple exercises where they can use that same arithmetic that they just figured out in other situations, such as in exercise 6 for a car going around a track, or exercise 8 for the measure of an angle. Now, as we progress more in the book and they have more and more ability, that's when we take more of the discussion out. The discussion will be shorter, and we include more examples and exercises and use that as our method for extending, for getting them to see and extend patterns. Finally, once they've caught that pattern or that concept, we use directed exercises to generalize the use of that concept or definition, and you'll see that's what we did at the end of this example here. The key point is that all generalizing and mental work is modeled. That is a must. That's what these students need. To deal with their lack of familiarity with complex numbers and modular arithmetic, the first two chapters of the book are exactly that: complex numbers and modular arithmetic. And as far as content, we really take them through the ringer on these two subjects. They see everything that you would want or expect them to see out of these two subjects. What we also did with these two chapters, we used them for two other kind of main purposes. The first was to develop their proof abilities and their exposure to different types of proofs. So not only do they see the content in these two chapters, but they see a lot of the theory behind it, and they work through learning how to do proofs in general, but also the specific proofs that you would see in these chapters. The second other purpose that we had for these chapters was to introduce them to abstract algebra concepts before they see them in the theoretical chapters, chapters 8, 9, and 10. For instance, we have some examples of this on the right side here. exercise 15 out of the complex numbers chapter. Here they're asked to look at the number systems they know, integers, rationals, reals, and complex, and they have to identify the additive identity, additive inverse, associative law, commutative law for these, as well as the equations that go along with those. A couple pages later in the complex numbers chapter, we show them through this table and preceding discussion that complex numbers under addition of complex numbers are exactly isomorphic to 2D vectors under the addition of 2D vectors. So you see that they're being introduced to these ideas and playing with the concept and the pattern in their head before they're even seeing a real formal definition. In the groups chapter, there's a great example of this. We introduce them in the middle of the chapter. We introduce them to the set of integers mod n, and after that, we take them through the process of figuring out that under modular addition, the integers mod n exhibit the properties of closure, identity, inverses, and associativity. And the clip that I have here is the end of that discussion where we kind of, this is actually the definition of a group. These two practices of having them work through their proof skills and work through different styles of proof and introducing them to the important algebra concepts that they'll see in the theoretical chapters, we do not only in these two chapters but in all the chapters leading up to those two. This was really one of the main methodologies in our book, was not only in a section or a specific chapter to have them see examples and exercises that reinforce a concept, but across the whole swath of the whole arc of the book to have them see examples and exercises that teach them a particular concept or definition. To give them an ease in thinking of terms and sets and functions, the next two chapters are exactly that. Chapter 3 is sets and Chapter 4 is functions. Now certainly we take them through the ringer as far as the content, but what we found is that it's not necessarily exposure to content that's going to get them to have an ease in thinking of terms and sets and functions. So what we really did with these chapters that kind of sets them apart is we use sets and we use functions that are not typical. That is, basically, we use sets that don't involve numbers, and we use functions that are not your typical algebraic calculus functions, just the things that they've seen repeatedly, because that's what they think a set and a function is about numbers. And we as mathematicians understand that obviously it's not necessarily that, but that's not where their mindset is. So in exercise on the right here in exercise 2 of the sets chapter, this is right in the beginning, part A. I ask them what elements are in the following set. The set P of elements X such that X is a regular polygon. So we're breaking in that idea. When we get to talking about subsets, one of the examples is the set of sons of parents John and Jane Doe is a subset of the children of John and Jane Doe. And the functions chapter, actually, when we talk about Cartesian products, so we can set up relations and functions, we define the standard deck of cards as the Cartesian product between 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace, and the suits, clubs, hearts, spades, and diamonds. When we introduce them to functions in the functions chapter, one of the first functions they see is this one. If we let people be the set of all people, alive or dead, then mother is a function from people to people. And to avoid ambiguity, we obviously, by mother, we mean biological mother. These are the kind of things that we did in this chapter, and this is key because to generalize the idea of dealing with a set or a function, you need to take it away from its numerical context. When they deal with symmetries and permutations, for example, how in the world are they going to understand the set of symmetries of a regular polygon? Or how are they going to understand the functional notation for permutations if they can't divorce themselves from thinking of these things in a numerical context? Similarly, as far as proofs go in this book, you can take a look at the list on the left. We take them through the ringer. We take them through all the types of proofs that they need to see. but exposure, just mere exposure to these proofs is not going to get them to be good at the proofs. And so on the right here I have an introductory example of how we got them to develop their proof abilities in this book. This is from chapter 1, the complex chapter. Their first proposition that they see is to prove that -1 has no real square root. Now, in this case, we're gonna show it to them, and what we do is we start off with what we call a long drawn-out proof. This is not just a paragraph proof, but this is a proof with all the gory details that should not be mentioned. We're showing them how to think through this proof, and then we give a streamlined proof right after that. So we're showing them not only how to think through it, but how to omit the details that you wouldn't want. And then exercise 2, right after the streamlined proof, is we ask them to imitate this proof to prove that -2 has no real fourth root. Proposition 34 of that chapter, de Moivre's theorem. At this point, we're assuming that they haven't seen induction. Now, instead of just merely explaining the proof and then asking them to imitate it, we take a different tact here. We explain what in the world an inductive proof looks like, but then we take them through a set of examples and exercises. I give 2 exercises here to show that, but we take them through a set of examples and exercises that end up being the inductive proof of de Moivre's theorem. We're developing their abilities not only through just merely exposition, but getting them to actually be involved in the creation of this proof. Now, as the book progresses and their proof skills get better, we slowly withdraw our hand. We give less to them as far as discussion and example, and we expect more out of them as far as proof creation goes. On this slide, we have some great examples of that. On the left side of this slide, this is an example from the sets chapter when we teach them to do element by element proofs. You notice on the first clip we give them a pure example with everything in it. On the second clip, which is just after that example in exercise 17, we ask them to prove a similar proof by filling in the blanks of the theorem. So we give them a full example, ask them to prove by filling in the blanks. On the top right, we have another example from the sets chapter, just a couple bit after this. Here we're showing them how to do an algebraic proof using set identities. We give them the full example, and instead of asking them to create a fill in the blank proof, we actually, in exercise 21, ask them to create their own proof. So they're expecting a little more out of them as far as creation wise. And exercise 43 here comes from actually our groups chapter, and here notice the difference. We take this even farther. Exercise 43 amounts to basically their example. Their example is a fill-in-the-blank proof that they have to go through and figure out. And then in exercise 44, we ask them to prove a similar proof, carte blanche, just out of their head and their abilities. So here's the big question: did it actually work? What we did to evaluate the effectiveness of this class is we had student surveys where we asked what they liked and didn't like, or what they appreciated and what they thought lacked about the 2 components of this class, what we did in the classroom and what we did with the textbook. We also looked at the grades from the spring 2010 class, which was taught with a more traditional abstract algebra book, and the spring 2011 class, which was taught with this book as we wrote it. As far as the surveys went, the feedback we got was very good. An example of this, I list here what they appreciated was the abundance and use of examples and exercises in the textbook in the classroom. And then when we asked what it lacked, a majority of students responded that they actually wanted more examples. Go figure. As far as the grades, you'll notice for the 2010 grades, there was kind of an even split between the higher and lower grades, but there was a large portion in the lower part, and you'll notice for the 2011 grades, though there was only 5 students, the majority of those students were in the A and B range. Now, obviously, these numbers are too small to make any statistical inference, but they're definitely suggestive at the least. Thank you very much.